Welcome to lecture number 10 for ECE 463 Modern Control, Dynamics of a Double Pendulum. Now what we've looked at previously was a single pendulum. That'd be like trying to balance a yardstick on your hand or taking a rocket from the hangar to the launch pad without it falling over. Now let's look at a double pendulum. This is you take a base or apply force on it, base slides back and forth. On top of that I have an inverted pendulum. On top of that I have a second inverted pendulum. Why you'd want to do that, I have no idea, but it is kind of cool, so why not? That also kind of leads into one of the cooler videos I've ever seen on the internet. So check this one out. This is a double pendulum. I've got the base. I can slide back and forth, apply force to it. On top of that, I have an inverted pendulum, one link. Connected to that is the second link. I'll fast forward a little bit. So this is the double pendulum, both pointing up. And these are the step responses. In this orientation, one link down, one link up. I'll give a step input, tell it to go left. Okay, tell it to go right. Coming back left. Here's the challenge. How are they doing that? How do they come up with a controller that can get it to go left and right for step input without falling down? And the most challenging of them, the double inverted pendulum. Give step input going right, going left, going right just to show off, back left. And to demonstrate this isn't a trick, you turn off the controller, it falls. So how do they do that? Well, to control a double pendulum, I first have to figure out what are the dynamics, and then come up with the feedback control law. The feedback control law comes later on in the semester. Today, just looking at what are the dynamics. So, here we go. To define the dynamics, first define the system. I've got a base with the link 1 connected to mass 2, connected to link 2, connected to mass 3. The angle Q1 is the angle of the first link relative to vertical. The second link, the angle is relative to the first link's angle. And X is in the vertical direction, Y to the right. Z-plane doesn't really matter. And my variables are X, the displacement of the cart, left and right. Kind of bad notation that X is Y, yeah, but we'll just go with it. So for the first link, its position is X, its vertical position is 0. The second link, its position is the first position plus sine theta 1. The second position is the first position plus cosine theta 1. The third mass, its position is the position of the second mass, plus sine theta 1 plus theta 2 in the right direction, and going up, it's cosine theta 1 plus theta 2. Okay, or using robotics notation, these are the variables. The first mass, position, second mass, third mass. Now take the derivatives. Derivative of y1 dot is x dot. y2 dot is x dot plus cosine theta 1 dot. x2 dot is sine theta 1 dot with a minus sign. Mass 3, y3 dot is x dot plus cosine theta 1 dot plus cosine theta 1 plus theta 2, theta 1 dot plus theta 2 dot. And x3 dot is minus sine theta 1 dot, minus sine theta 1 plus theta 1 dot plus theta 2 dot. Okay, so we have positions and velocities now. With that, I can define the kinetic energy. That's the position of the first mass, 1/2 mv1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared. The first mass, its speed is just x dot squared. The second mass, here's your x squared, x2 dot squared, y2 dot squared. Third mass, x3 dot squared, y3 dot squared. And all masses are 1. Now simplifying, I get cosine squared plus sine squared is 1. Cosine squared plus sine squared is 1. Cosine squared plus sine squared is 1. So those simplify. I get some cross terms, which mostly cancel. And after some algebra, this is the kinetic energy. Fairly lengthy, but not completely absurd. The potential energy is the potential energy of the first mass plus second mass plus third mass. Gives you 2g cosine theta 1 plus g cosine theta 1 plus theta 2. From that, we can form the Lagrangian. So I've got the kinetic energy minus potential energy. Now to find the dynamics, I need to take 3 sets of derivatives. The partial with respect to x gives you the force on the base. Partial with respect to theta 1 is the torque on the shoulder, which is 0. Partial with respect to theta 2 is the torque at the elbow, which will also be 0. But you could add motors there if you wanted to, but this system doesn't have that. So starting with the base, the force on the base is the full derivative with respect to time of the partial of L with respect to x dot minus the partial of L with respect to x. Partial of L with respect to x dot is, here's an x dot, gives you 3x dot. Here's an x dot, plus 2 cosine theta 1 dot, and here's an x dot, plus cosine theta 1 plus theta 1 dot plus theta 2 dot. And there are no x's, no x's anywhere, minus 0. Now take the full derivative, gives you 3x double prime, plus chain rule, partial of the second term is 2 cosine theta 1 double prime. Derivative with respect to the first term is minus 2 sine theta 1 dot, gives it theta 1 dot squared. Cosine theta 1 plus theta 1 double prime plus theta 2 double prime, plus, actually minus, sine theta 1 plus theta 2 times theta 1 dot plus theta 2 dot squared. So there's the force on the mass. That's one set of equations. Second set of equations, the torque on angle 1. Again, here's the Lagrangian, just to remind us. The torque on the first link is the full derivative with respect to time of the partial of L with respect to theta 1 dot minus the partial of L with respect to theta 1. Partial of L with respect to theta 1 dot is, here's the theta 1 dot, 2 theta 1 dot, here's the theta 1 dot, 2 times a half theta 1 dot plus theta 2 dot, here's 1, 2 cosine 1 theta 1, 2 cosine 1 x dot, chain rule, cosine theta 2 times theta 1 dot plus theta 2 dot plus cosine theta 1 dot, here's theta 1 dot, plus cosine theta 1 plus theta 2 x2 dot, minus the partial with respect to theta 1. And let's see, here's the theta 1, minus 2 sine theta 1 x dot theta 1 dot. Let's see, here's the theta 1, minus sine theta 1 plus theta 2 x dot theta 1 dot plus theta 2 dot. And here are theta 1s, your gravity terms. Now take the full derivative. I get 2 theta 1 double prime, theta 1 double prime, theta 2 double prime, chain rule, minus 2 sine theta 1 x dot theta 1 dot plus 2 cosine theta 1 x double prime minus sine theta 2 dot theta 1 dot plus theta 2 dot plus, derivative the second term, cosine theta 2 theta 1 double prime plus theta 2 double prime minus sine theta 2 dot theta 1 dot, chain rule, plus cosine theta 2, theta 1 double prime, minus sine theta 1 plus theta 2, x dot, theta 1 dot plus theta 2 dot, cosine theta 2, x2 double prime, with the gravity terms. Now the torque with respect to theta 3. Again, here's the Lagrangian. The torque with respect to the third joint is the full derivative with respect to time of the partial of L with respect to theta 2 dot minus the partial of L with respect to theta 2. Partial of L with respect to theta 2 dot is nothing, nothing. Here's the theta 2 dot. Gives you theta 1 dot plus theta 2 dot. Nothing, nothing. Here's theta 2 dot. Plus cosine theta 2, theta 1 dot. Here's the theta 2 dot. Plus cosine theta 1 plus theta 2, x dot. Minus the partial with respect to theta 2. So let's see, nothing, nothing. Here's a theta 2. Minus sine theta 2, theta 1 dot plus theta 2 dot times theta 2 dot plus theta 1 dot. Something like that. Here's the theta 2. Minus sine 1, 2. X dot, theta 1 dot plus theta 2 dot. And here's the theta 2. Plus g sine 1, 2. Now take the full derivative of this. Gives you theta 1 double prime, theta 2 double prime, chain rule, minus sine theta 2, theta 2 dot, theta 1 dot, plus theta 1 double prime, chain rule, minus sine theta 1 plus theta 2, theta 1 dot plus theta 2 dot times x dot, plus cosine theta 1, 2, x2 double prime, and bring out the minus sign. Okay, so we have three sets of equations. This is the dynamics of that double pendulum. If I know the force, torque on the first link, torque on the second link, which these are going to be 0, the position, velocity, angle, angular velocity, theta 1, angle, angular velocity, theta 2, I can calculate theta 1 double prime, x double prime, theta 2 double prime. But no acceleration, integrate I have velocity, integrate I have position. I can tell you what the dynamics are. But note, this is a rather nasty set of nonlinear dynamics. However, even that being so, Lagrangians were able to come up with the answer, and it only took 12 minutes 42 seconds, according to my clock. Other methods don't get you there. That's one of the real advantages of Lagrangian dynamics. I can find the answer. May not be easy, may take a lot of calculus, but we've had 4 years of math. It's calculus we can do. So another way to write the dynamics, this is standard for robotics. I have a mass matrix times acceleration is the Coriolis force matrix. That's kind of like an ice skater, bring your arms in as he spins. The energy has to stay constant, so as the rotational inertia drops, the speed has to increase. A gravity matrix and a torque matrix. So taking these dynamics, rewriting them, I'll put all the accelerations on the left, all the other terms on the right. There's a first set of equations, second set of equations, third set of equations. Yeah, trust me, that's how they work out. Now let's put this in matrix form. If I put this as a 3 by 3 matrix times the acceleration, I get this. This is the mass matrix. This is the Coriolis force matrix, function of your theta 1 dot squareds, theta 2 dot squareds, so on. The gravity matrix and the torque matrix. One of the torques is a force, but kind of generalized torque matrix. So if I know position, velocity, I can calculate all these. I can calculate the mass matrix, take the inverse of that, and find the accelerations. That's kind of how the simulation works. This is the code, cart2 display, cart2 dynamics. Cart2 display is if I tell it, here's x, theta 1, theta 2, it draws it on the screen. 0 position is pointing up. Cart2 dynamics is this part. I tell it, here's the state of the system, position, velocity, torque, forces, and then it calculates, this is the acceleration. Again, I'm assuming the torques are 0. And if I want to do the double gantry system, kind of same idea, all I do is just change the sign of gravity. So if gravity is pointing up, I get a minus g. Gravity is pointing down, put in a sign difference, and change the display routine so that 0 is pointing down. It's now pointing down. So I kind of get 2 for 1. An inverted gantry system, double gantry, and a double cart. With that, I can sit there and simulate it. So here's the double cart system. I've got 2 links. If I have no control input, it falls, not surprisingly. Bug. If I do the double gantry system, just change the direction of gravity. And here I'm using a PD controller. Proportional gain is 10. Derivative gain is 10. I'm trying to go over here. Double gantry, you can't actually stabilize it with a PD control. The double pendulum, you can't. But using those same dynamics, kind of see what's happening over here. I calculate the input, given the input, and that's the force on the base. And the state, I can find the acceleration. Integrate, I get the states. First 3 states are position, last 3 states are acceleration or velocity. Time goes forward 10 milliseconds, repeat, and you get your animation. So here's a question for you. What are the eigenvalues? Again, the eigenvalues only apply to linear systems. This is nonlinear. So to linearize it, I need to pick my operating point. In this case, can be either straight up or straight down. Find the linearized dynamics at that operating point. If I have it pointing straight up, then here's your mass matrix. Here's the gravity matrix. The Coriolis force matrix has all these higher order terms. That's roughly 0. Intergeneralized input. Take the inverse of the mass matrix, multiply on the left, put in state space form. Again, the first 3 states are position, last 3 states are velocities, derivative of positions, velocity, so get this 0 identity matrix. Here's where these dynamics come into play. I now can find the eigenvalues of that matrix. And the eigenvalues are 0, 0, minus 6.8, minus 3.5, plus 6.8, plus 3.5. The open loop system is unstable, which isn't too surprising. If I simulate the double pendulum with no input, it falls down. And the eigenvalues tell you how fast it falls. One of the poles is at plus 6.8, so it actually falls pretty fast, as e to the 6.8 t. If you reverse gravity, then this becomes the A matrix. Its eigenvalues are 0, 0, plus minus j 6.8, plus minus j 3.5. So if I turn off the input, here u equals 0, give it a small initial condition, and watch it go, it'll swing back and forth. And it's actually swinging back and forth with 2 frequencies. I've got the double pendulum. One frequency is 6.8 radians per second, and the second frequency, I forgot, is something else. There, 3.5 radians per second. And kind of watch it swing back and forth. So the linearized model is working fairly well. For small perturbations, I can tell you how it's going to behave. This shows off a little bit better. I just increased dt to 0.02, speeds up the system. You can see it oscillating back and forth better this way. So in summary, the Lagrangian formulation of dynamics, again, works for us. Not real fun, kind of long, lengthy derivation. The derivation is a bit nasty, but it does work. But that's one of the reasons we engineers take so much math. If you want to know the dynamics of a double pendulum, there's not much way around it. Once I get that dynamics, Then I can start looking at designing feedback controllers to stabilize that. But that'll come later in the semester. Right now, we've just got the dynamics, and they are here they are, the dynamics of a double pendulum.